aspects that limit the ductility of metallic glasses by way of damping out the shear band shear localizations. And this was primarily the work that was done using atomistic calculations. And a more recent work, as I said, is in the area of reprocessable thermosets, which can be granulated, pulverized, and reprocessed cyclically, so that you can use their functionality for multiple number of times. And we are looking at it from the viewpoint of granular mechanics. Incidentally, this is an area that I'm looking to expand, and we are looking for a couple of new graduate students to work on this area. So let me get into the theme of the talk. Some of you might be aware of this first Sandia National Challenge, Fracture Challenge, that was back in 2013, 2014. And the report that came out, which was published in International Journal of Fracture, compared the experimental results that were kind of blind tests that were done by a group in Sandia and UT Austin, which was thrown out as a challenge for modeling groups to try and predict in terms of the number of quantities of interest, but one of them being the force displacement or the force crack opening responses. And you can see there is a spectrum of responses that you can imagine. Some of these are based on completely phenomenological or empirical models. Others are based on highly resolved computational frameworks, including peridynamics, for example. And you can see that many of them capture some of the coarser details, but none of them really, or most of them don't kind of match the exact finer details of the experiments. And not surprisingly, the kind of observations that were made was the need to develop better constitutive models, couple them with improved computational methods to be able to capture the necessary details of such fracture processes. So if you go into the basics of ductile fracture or ductile failure, and this is a beautiful paper I would recommend to anybody who is interested in understanding brittle and ductile fracture, by my colleague and collaborator, Professor Amin Benzerga, and his collaborators, Professor Pinot and others, where they talk about fundamental aspects of both experimental and theoretical aspects of ductile failure. But broadly speaking, you can think of failure occurring by two modes, so to say. One is the one that I'm going to talk about, which is by internal nucleation, growth, and coalescence of voids that you see on the right side of this schematic. And what happens is the voids nucleate, they grow, they coalesce into one another, and they form damaged zones, which also immediately introduces us to the multiple scales at which these processes occurs. Plasticity, which is driven by slip and sometimes by other mechanisms like twinning that I'm going to talk about, they interact with defects in the form of the internal porosity or second phase particles that lead to nucleation of voids. These voids then form zones of damage, which we call as mesoscopic zones of damage, which then interact with component scales to form macroscopic fracture phenomena. So that's something that is interesting. And one of the metrics that comes up in this is a scalar called stress-triaxiality, which is simply the ratio of the mean stress to the equivalent stress shown in this expression over here. The other mechanism or the other mode is by way of instability, typically referred to as shear instability, but I'm not going to talk about that today, and not, at least not in great details. But then what causes things to get complicated in terms of fracture? Well, anisotropy in the context of plastic anisotropy becomes rather critical, and some of the works of Professor Kerala Verma in Indian Institute of Technology in Chennai, his work and others have shown very nicely through theoretical modeling and computational modeling how to incorporate net plastic anisotropy into continuum porous plasticity models. But at the finer scale, what drives anisotropy is crystallographic anisotropy, or that comes up as texture effects, then the distribution of flaws and the distribution of the shapes of flaws. As you can see on in these TEM pictures on the right, you may have second phase particles that are quite randomly distributed. They have different shapes, they have different size distributions that can cause fracture at their interfaces, as shown in the picture below. or the particles themselves can fracture, which can give rise to various different shapes of initial voids. So how to couple all these things together is a very interesting problem. Add to that the question of, sorry, I think there is a background noise here. Uh, I think there's some background noise. I'm not sure where it's coming from.
Yeah, there was some background noise. I think it's okay now, Sharendra. Yeah.
Okay, right.
I think
All right.
somebody switched on his mic.
Oh, okay, okay. So in addition to that, more recently advanced engineered microstructures like the nanotwin microstructures have come to the fore, which bring in substantive complexities to the damage and failure process. Become challenging problems when it comes to incorporating them into constitutive theories. Or we may have crystallographic complications. In this case, for example, the particular type of crystallography that we are referring to is hexagonal closed pack structure shown here at the bottom right, which can result in highly complex stress strain responses that are orientation dependent, plus potentially tension compression asymmetry, depending upon different mechanisms that can get activated, depending upon how you load the systems. That can have a tremendous effect on how damage evolves. For example, if you see at the collage of pictures that are shown at the bottom for magnesium and titanium, you can see that the shapes of the voids and the final process of deformation and cracking occurs can be quite uh, uh, dependent on the local crystallography or local microstructural detail. And this is some of the things that we are interested in capturing. So I'm going to focus primarily on HCP materials. There are a number of HCP materials that are technologically important, but the particular material that we are going to talk about here is magnesium because of its remarkable properties, physical as well as uh, biomechanical properties. Uh, but one of the things is because they have a HCP crystallography, in addition to the conventional mechanism that we know of in the form of slip in many materials, that many materials undergo. Materials like magnesium, they undergo what is called as twinning, where you get a sudden reorientation of part of the crystal relative to its neighborhood, and that orientation creates a mirror symmetry between the parent material and the reoriented material, which we call as twin. Okay, so there is slip process and twinning process, and in magnesium, these processes become very important. So if we take a step back and ask, what are the models that are available currently in the context of how anisotropy can be brought into the context of porous plasticity? There are a number of very sophisticated models, but most of them start out being remnants of the very seminal work that was done by first by Rice and Tracy and then by Gerson, to understand how a spherical void sitting inside a spherical Mises matrix would evolve under macroscopic boundary traction boundary conditions or loading boundary conditions, which was then extended by Benzerga and co-workers to account for hill-type anisotropy, but with spherical voids. And then subsequently, there have been developments done by Professor Benzerga and his group, and then Professor Kerala Verma at IIT, to understand how shapes and orientations of voids can be brought into the fold of defining yield functions that account for those effects, including the porosity. So a typical porous yield function for porous plasticity looks like the equation that is shown at the bottom, where you have a quadratic term that depends on the equivalent stress, and you have a term that goes exponentially with the mean stress that is shown in the bracket after the hyperbolic cosine function. So the ultimate objective is to be able to figure out how to bring the role of crystallography and the finer details of interactions between slip and twinning mechanisms into framework that can be presented in the manner very similar to these continuum models of porous plasticity. And so there are a number of these models without the porosity built in that capture plastic anisotropy. Here is a quick snapshot of that. I'll not go into the details, but one of the most uh, interesting early models was that by Hill, which is called as Hill type anisotropy, which is shown here, highlighted here in the blue. And the reason why it becomes interesting is because you can start extracting some indices out of it. And one of the indices that Dr. Benzerga, for example, has presented in his work is this scalar index, what he likes to call as anisotropy effect on ductility, which is AED index, which is a combination that creates an invariant of the Hill coefficients shown in that Hill yield function. Plus, you can come up with metrics that describe shear anisotropy, and these are interesting because now you can use these some of these indices to define to bring them into the fold of porous plasticity, and you can quickly see that the rate of porosity growth f dot goes as within the exponent. So this h, which describes the scalar, which is a scalar descriptor of a particular type of anisotropy, plays a very important role in the rate at which voids would grow. That's something very interesting. So in some sense, this AED index tells us what anisotropy will do to damage by void growth. And in addition, to some extent, but not to the similar extent, the shear anisotropy ratios will give us some idea of how the anisotropy would lead to shear instability or potentially lead to shear instability. I think the latter part is not as well developed as the former, but nonetheless, there are some developments that are going in that direction. This is again the snapshot of Dr. Kerala Verma's work back in 2011 that describes how anisotropy can lead to can couple into the porosity growth. And you may have material that is anisotropic. You can have anisotropy that is driven by the shape of the initial voids. But then when you combine these two ideas together, you can see that the net effect or the overall effect is not that of simple superposition, which is expected because these are highly nonlinear dissipative processes that are going on. So some very interesting observations. And now if you throw into the mix the role of crystallography and deformation mechanisms, it remains to be seen how these evolutions come about, particularly in the context of HCP materials. So what is so special about HCP materials? Well, in the context of magnesium, we have slip processes, and the different types of slip mechanisms are shown over here in the context of crystallography. You have basal slip that is shown on the left. Then you have prismatic slip, which is shown as a vertical plane, the flat face. Then you have a pyramidal A slip that is shown as an inclined plane, the same picture in the middle. And then you have a pyramidal C plus A slip. And there are these in total they constitute 18 slip modes. There are 18 slip systems. But then because of the low symmetry of these materials, some of these mechanisms are mutually exclusive. And so if you have a loading state that excludes any or precludes any type of deformation by these modes, it gives rise to what is called as twinning. And then there are two types of twinning modes. One is called as the extension twinning mode, or 101 bar 2 type twinning mode, as we call it in the material science community, where if the C-axis, the vertical axis of the crystal, is undergoing net extension, then that twinning mode gets activated. Or you have a contraction twinning mode, which is called as the 101 bar 1 twinning mode, where the C-axis, if it undergoes net contraction, then you get that contraction twinning mode. And there are a total of 12 types of total twin systems that are available. So in all, we are talking about at least 30 slip and twin systems that can define the mechanical response of a single crystal. And they go from being very soft to very hard plastically. To give you an idea, this is a typical range of critical resolved shear stresses of different slip and twinning modes that we see in pure magnesium. You can see that basal slip is like butter. It's extremely soft and easy to activate at the smallest application of load for even small crystallographic misorientations. But then on the other end of spectrum, you have contraction twinning that is 2 orders of magnitude harder plastically to activate. So what that does, as I mentioned earlier, is that it creates a remarkable landscape of anisotropic responses and tension compression asymmetry not only at the single crystal level, as shown at the top picture of the stress strain curve, but also at the polycrystalline level, where the polycrystal response is now modulated or mediated by the textural effects. So the coupling between crystallography and texture plays out in the response of polycrystal. But you can see some very similar qualitative behaviors that between single crystals and polycrystals in that sense. What does it do? Well, if you look at some of the early experiments that were done on certain types of magnesium alloys, here we are talking about a particular type of magnesium alloy, AZ31, under uniaxial loading. What this particular experiment showed was, or suggested, was that there were different regimes on the fracture surface that were seen, and at the smaller scale they could be related potentially to the mechanisms that were activated in those regions. For example, the regions that were seen to have dimples, which is classic of what we think of ductile failure surfaces, had largely the extension twins were absent in that region. So there was no evidence of extension twinning in those regions. On the other hand, regions that exhibited dimples that were sheared, the authors observed double twins inside twins. And I'll talk about that briefly later on in this when I show the results. On the other hand, the regions that showed very flat facets of fracture indicated a significant amount of twinning. Now, how profuse is profuse remains to be seen, but essentially what these ideas suggested, initially at least, was that twinning is bad when it comes to fracture, because you start getting brittle type fracture surfaces if you have extension twins that come up. And this has been quite prevalent story in the community, particularly in the materials community, saying that, well, we should get rid of twinning somehow. But then some of the very interesting and careful experiments that were done by Professor Narasimhan and his group on 3-point bend experiments of single crystals suggested a different story. Indeed, what they found was that if you have really profuse twinning, that can serve as a very potent dissipative mechanism and can give rise to significant toughening of material. And so you have potentially a conflicting scenario where one set of experiments show twinning being detrimental to toughness and ductility. In other case, you are seeing twinning to be quite a promising mechanism. And so, these are things that keep us awake at night. Finally, a couple of more experimental evidences. These are the experiments done by Professor Benzerga and his former student, Baba Kondori. Beautiful set of experiments where notched circular bars were used as specimens to control the nominal triaxiality shown on the x-axis over here, and two different materials, magnesium alloys AZ31, which is slightly more plastically anisotropic, compared to a magnesium rare earth alloy WE43, which is much less anisotropic. And what they found was that depending upon the stress triaxiality, one sees quite different forensics of fracture. At the low levels of triaxiality, they reported some type of quasi-ductile or quasi-brittle type fracture surfaces, and in fact they observed shear localization, which is quite unheard of in most ductile materials under axisymmetric loading conditions. But then at moderate range of triaxiality levels, the ductility is actually goes up. The fracture strain is actually larger compared to the uniaxial cases. And then as you go along the scale of higher triaxiality, the fracture strain drops as like conventional materials. And but what was very interesting was that a material that is more plastically anisotropic, AZ31, showed higher fracture strains compared to WE43, that is less anisotropic. So the notion that anisotropy could be bad for ductility is clearly not the case. I mean, you can have materials that are anisotropic but possess better ductility. And this was also shown through some theoretical and computational approaches earlier on, but then you can clearly see that in the experiments as well. Final experiments over here on how voids or holes connect as a function of the hole orientation relative to each other. Theta is the orientation between two adjacent holes subjected to in a specimen that is subjected to uniaxial tension, And what was observed is in a material like copper that many of us are much more comfortable with, there is a clear trend between the loading, the hole orientations and the fracture strain. Whereas when it comes to magnesium, the results are all over the place, and you can see that there is a big scatter in the results as well. And the reason for that is because if you see the finer details of these holes can very quickly merge into one another by cracking across, and these crackings are presumably because of twins that are developed in those regions that lead to premature merging of these holes. So with that background, what we have is to understand how anisotropy couples into applied stress states and cause failure. And in this case, what we are going to do is we are primarily going to look at crystallographic aspects of anisotropy. So we are going to deal with single crystals. Later on, if time permits, I'll talk a little bit about textural effects. But then the load conditions, we are going to primarily focus on tensile load states defined by stress triaxiality with no intrinsic shear deformation or shear loads, so the load parameter, as we call it, is -1, and failure is going to be discussed in the context of void growth and nucleation. We are not going to tackle void growth and coalescence. We are not going to tackle void nucleation in this case. What method we use over here? We use crystal plasticity. So if you take a typical snapshot of an atomistic viewpoint of a HCP single crystal, what you see is there are slip mechanisms, there are twins that are developed, and if you smear them out using crystal plasticity, you talk about twin systems and slip systems, and we put them in the finite deformation plasticity context by multiplicative decomposition of the total deformation gradient, FE/FP, which then allows us to write the plastic velocity gradient as a contribution that comes via slip in the untwinned region. I call that as matrix, and then the twin in the untwinned region, and finally the slip in the twinned region. F over here indicates the current twin volume fraction on a particular twin system beta. And as I mentioned, there are two types of twin systems, but then each of them have 6 twin variants. So the total number of twin systems is 12, NTW is 12, and S is 18. So the total number of slip and twin systems at a given point inside a material is 30. Okay, so it's a computationally expensive calculation there itself. I'm not going to go into the details of the model any further, but suffices to say that this was the work that was done by a former postdoc of mine, Dr. Jing Zhang. She's since moved back into industry, and then she's been working on some of these ideas in the context of automotive applications of magnesium alloys. So here is the protocol that we are using. We are going to look at three-dimensional unit cells. These are cubic cells with a spherical void inside it. I'm showing just the 1/8 portion of it, but we actually model the entire cell to discount any constraint due to symmetry. So we allow for any asymmetry breaking in this by way of deformation, and being subjected to primarily tensile loading states, where the primary loading direction is in the along the y-axis, and the stresses along the x and the z are controlled in terms of ratio to control the stress triaxiality. We are going to look at two canonical orientations, one of them being a prismatic orientation, where the 1, 2 bar 1, 0, the prismatic axis is oriented along the y direction, and in the other case, the c-axis is oriented along the y direction. And as you can imagine, because the c-axis is under extension in the second case, we would expect extension twinning to be the primary driving deformation mechanism. So with that, and the material parameters that we are going to use are typical of a magnesium material. Okay, so let me talk about some of the strain responses. Nothing really quite interesting per se until you start looking at the finer details of it. What you see is that the dashed response is that of a pristine crystal, meaning that there is no void inside this crystal. And then all the solid curves are with voids, a single spherical void with all periodic boundary conditions. So we are accounting for inter-void interactions over there. and at different levels of stress triaxiality shown by different colors, 1/3, 1, 2, and 3. What we see is at high levels of triaxiality of 2 and 3, we see what we expect. We see a stress that is limited by the rate at which the void is growing. The superposed plot is showing porosity growth, the rate at which, or the growth of void over here, the normalized rate of growth of void. And you can see that at uniaxial, under uniaxial loading condition, the void practically doesn't grow. It remains flat. It is growing at a very slow rate, remains practically flat. But at triaxiality of 1, you start seeing a void that is growing rather rapidly, shown by the red color. But at the same time, the stress strain response is also increasing despite the void growing rather rapidly. And it is actually hardening. It is hardening much more than the pristine crystal. And before it starts to soften up and then fail. The black circles are when we find the voids at the cusp of onset of coalescence between their neighbors. Okay, so that's quite interesting. So at intermediate levels of triaxiality of about 1 or so, we see a net hardening effect, which we call as the void-induced hardening effect, because the void is still growing, yet the strain response is that of a hardening type. And the reason that happens is because of the deformation mechanisms that activate around the voids. So this is a snapshot of what kind of deformation mechanisms can activate. These are called relative activities, shown by this equation xi or zeta, sorry, which is the volume averaged slip rate, or the activity rate of a particular activity divided by the total slip rate activity at any given or in the given volume. And so in a material that is pristine, you see that for this particular loading, as expected, because we are loading it along the prismatic axis, prismatic loading shown by blue is quite dominant, with very little contribution from any other slip mode, given that it's a single crystal. But when you start loading a voided single crystal at triaxiality of 1/3, you see that still prismatic is quite dominant, but there are other mechanisms that are getting activated now. If you increase the stress triaxiality, you start seeing that other mechanisms are starting to play a more dominant role, and the relative role of prismatic slip is getting diminished, to the extent that at a much higher triaxiality of 2, you see that there are much harder slip modes, as you can imagine. The pyramidal C plus A slip mode, which I mentioned is is one of the hardest modes plastically, starts getting activated, and that produces the hardening effects that we just saw. When you go to the other loading orientation, C-axis loading, you see something very interesting. The first, you see two yield kind of behaviors. At the very early stages of deformation, you see yield happening at a very low level of stress, because extension twins are quite soft, as I mentioned earlier. But then after twinning has occurred, during twinning, there is a small level of hardening, beyond which, when the crystal gets oriented or reoriented into a twinned region, you see a sudden surge of the stress. And that surge is seen even in the pristine crystal. But what is quite interesting is that in the voided crystal, you start seeing a much higher stress elevation, macroscopic stress. So voided crystal is stronger than the pristine crystal, which is quite intriguing. And that is true both at uniaxial case, but also at moderately high levels of triaxiality of about 1 or so. And only when the stress triaxiality gets to much higher values of 2 and 3 do we see a response that is quite diminished relative to the lower levels of triaxiality. And so the question becomes, why is that? If we look at the void response, in fact, at uniaxial conditions, the void starts to close up, even under purely tensile loading state. So there is a closure of void that occurs. But when you go to higher levels of triaxiality, for example, look at the red response of the porosity. The porosity is growing quite rapidly, yet the response is quite strong or hard. Again, void-induced hardening effect. What is also interesting is that in the regime of twinning, which you see on the left side, up to about a strain of 6% or so, the void growth is quite insensitive to triaxiality. The rate of void growth is quite insensitive to triaxiality. Immediately as reorientation occurs, when twinning is completed, you see that the void responds to that twinning, exhaustion of twinning, in a remarkable manner, which now is sensitive to the applied load state. And the reason that happens is because, again, if we look at the relative activity plots, we see that for pristine crystal, as expected, the initial deformation is entirely dominated by extension twins. And at about 6%, when twinning is complete, other modes start to activate because the crystal has reoriented into a new orientation. By the way, this new orientation is about close to 90 degrees from its parent orientation. So it's a remarkable amount of reorientation of a crystal with respect to its parent region. But when you go to the voided crystals, you start seeing rather rich landscape of deformation mechanisms that get activated after twinning is complete. Twinning is still the most important mode because it's soft, but after twinning occurs, what kind of deformation mechanisms occur around a void is dictated by the stress state. And higher the stress triaxiality, the more rich the landscape is in terms of their interaction of different deformation mechanisms. So that's the macroscopic part, but what happens really around the void? And so what I'm going to show you here is a movie of how different deformation mechanisms activate around a void. And what we are seeing here is a plane of coalescence. So the primary loading direction is coming out of the plane of your screen. You're seeing one particular cross section in the xz plane, y being the loading direction, primary loading direction. We are looking at a stress triaxiality of 1, and this is for the prismatic loading, which doesn't typically have twinning as the primary mode of deformation. And each of the halves that you see are going to show you the activity of a particular mechanism: pyramidal C plus A, prismatic A, basal, contraction twin, extension twin, and the central half over here on the right side is going to show how it affects the equivalent plastic strain. So let me play the movie. It's going to be quite busy, but let me just play the movie. And what you see is that prismatic loading becomes dominant as expected, but as deformation starts to activate, you see other mechanisms like pyramidal C plus A or contraction twin and extension twin being activated in different parts of the region. Okay, and you can see that regions that are undergoing heavy extension twinning around the void are initially they're deprived of other mechanisms like prismatic axis and prismatic slip and so on and so forth. But what you also notice as the void is starting to grow now, and this is how the void will coalesce with its neighbors now, you see that one of the ligaments in the x direction, for example, is much thinner than the ligament in the z direction. So even the coalescence is anisotropic. You're seeing material or the voids preferring to coalesce in a particular direction with its neighbors compared to the voids along the other axis. So there's a significant anisotropy potentially anisotropy in the fracture process as well. We don't take it all the way to the fracture because we don't. Our computational model doesn't have the capability to model fracture, but you can imagine that the ligament is going to then completely thin down, and then the voids are going to coalesce in a given direction. If we take a look at what happens at higher triaxiality level for the same loading, you see similar, but now you start seeing localizations in the context of basal slip. You start seeing that the initial localization of basal slip in the void kind of dictated the shape of the void. The shape of the void, which started off being spherical, now has grown into something like a cube. And you start seeing these bulbs that come out of the void, which is indicative of the strong strain localization that is getting that is dominating the shape of the void. So again, what you saw as relative activities now play out as the distribution of those deformation mechanisms around the void on a particular plane. Of course, it's a very three-dimensional process, but it's quite hard to show that entire three-dimensional process. But this is the potential plane of coalescence, which is what I'm showing over here. As I mentioned, double twins have been thought of as quite detrimental to fracture, and there is some experimental evidence of it as shown in the picture on the right over here. What our simulations also show is that as deformations start to occur, we can the beauty of crystal plasticity is that it can naturally pick up these emerging behaviors emergent behavior. So we indeed observe some kind of double twinning where you have extension twins and contraction twins. So within extension twins, you get contraction twins on one side, on the equator, as I would call it, and on the pole side of the material of the void, you see extension twins inside contraction twins. So you get different types of family of double twins in the regions around the void, or in the very near vicinity of the void. So those are some really interesting results that we can capture through these high fidelity simulations. In the interest of time, I'll move on to what happens under C-axis loading just at the higher triaxiality level. So again, the same picture, but now you are looking at the response of a crystal under C-axis loading at a triaxiality of 2. Again, the same plane that I'm talking about. But now what you would expect is, because we are loading along the C-axis, extension twin is going to dominate the response quite a bit. And then only when the extension twin is completed would we see other mechanisms getting activated. So I'm going to play, and the extension twin, I would warn you that the extension twin gets out of the way quite quickly, but then other mechanisms start to activate after that. So let me play the movie. You can see extension twin is dominating. Once it is exhausted, other mechanisms start to activate, primarily pyramidal C plus A and basal slip. And what it does is rather intriguing. At least we found it quite remarkable in the first time that we saw this result, is that you start seeing that the void is actually sharpening up. Okay? And this is something that is not found conventionally in materials or voids undergoing growth in conventional materials, at least as predicted by continuum theories, because typically plasticity is a relaxing mechanism, and it blunts out any sharp features around it by creating plastic relaxations around it. But here we see sharpening of voids, and the reason why these voids sharpen is because there are twin boundaries that intersect with the void surfaces. And if you have particular types of twin boundaries that intersect with void surfaces, they lead to plastic localization at those intersections, and that is what is giving rise to this sharpening effect, which, if you recall, some of the kind of gives us some remnants of what those whole experiments showed in terms of sudden merging of voids by cracking between the intervoid ligaments. That may be something that might happen in such scenarios. Okay, so I'll summarize quickly this part, and then if there is still time, how am I doing here? Maybe in the next 5 to 10 minutes, I will talk about some of the more recent work that we are doing as an extension to this work. But the idea is that these deformation mechanisms do exhibit some features that typically cannot be captured or may not be captured by current theories that we have in anisotropic plasticity of porous materials. And hopefully some of these high resolution simulations will motivate developments of improved theories that can lead to better predictions of materials undergoing failure under highly anisotropic and plasticity and potential tension compression asymmetry, because of the different mechanisms that get activated depending upon whether the material is under tension or under compression loading. But the other thing that I would like to mention is that this idea of void sharpening and its implications on premature failure is something worth investigating further. So in the next few minutes, I'll just quickly talk about how do we go from high resolution to high throughput. And the idea is that we want to capture some of these ideas, but not spend so much time doing these computationally expensive calculations. At least when we go from single crystal to polycrystal, if I were to model a void with explicit representation of grains around it, that such a calculation would be exorbitantly expensive and quite untenable. So one of the things that we have been doing is to take a slightly different route, and look at response. First, try to collate all the responses to understand the role of textural variability on the anisotropy or the macroscopic anisotropy and tension compression asymmetry in polycrystalline materials by doing numerical experiments, systematic numerical experiments, and then project the role of the macroscopic anisotropy and tension compression asymmetry on damage, either by porosity evolution or by shear instability. And what we have done in this recent work that we have just published with a former student of mine is that we have looked at a number of different textures in polycrystalline sense, going from extremely strong textures shown in A over here and to extremely weak texture shown in K at the very bottom. And the idea is as follows. We take a kind of a statistical volume element of polycrystals, explicit representation. Imagine that to be an RV from a rolled plate with orientations that are given by the roll direction, the transverse to the rolling direction, and the normal to the rolling plane, L, T, and S respectively. And we incorporate textural variability in these calculations by playing with Euler angles, and then look at their responses, macroscopic responses, their microscopic underpinnings in terms of the relative activities, and then map these two into the three-dimensional anisotropy by considering different loading orientations, uniaxial conditions, by the way, and then use an existing damage theory to find out what kind of implication it has, such an anisotropy has on predicting failure. So what we have done is we have looked at 11 textures, we have looked at 6 loading orientations, we have looked at 2 crystallographic anisotropy sets, one representing pure magnesium, another representing a magnesium alloy. We have looked at 2 different loading states, tension and compression, which gives us total of 264 simulations. Okay, and using the entire set of results from these simulations, then we are going to put them into a framework or a model to allow us to give some ideas about how this can affect damage. I'm not going to go into the details of the responses. Suffices to show that the kind of responses we can generate over here is not just the stress-strain response, but also talk about deformation anisotropy at the macroscopic scale and its underlying role of deformation mechanisms, both in tension and compression, for principal axis loading, meaning loading along the primary material directions, and off-axis loading conditions, which is 45 degrees to the principal material directions. We collate all these responses and we put them into a simple hill-type anisotropy model. Admittedly, this is quite simplistic compared to the complex response of a typical magnesium-type material, but this is a start. And the idea is that using the full 3D characterization, numerical characterization of these materials, we can extract these indices, the AED index that I mentioned to you earlier about, and the shear anisotropy ratios, which represent respectively how anisotropy would affect damage by void growth and the susceptibility of such a material, of a particular material, to shear instability. So what we have done is we have computed these indices from those calculations that I showed you before, and we have plotted those indices as a function of different textures. Okay, and once we have plotted these for different textures, we can take kind of steady state values at large magnitudes of strains, and then plot them as a function of texture. So AED index here is plotted for different textures at the steady state value. Similarly, the shear anisotropy ratios are plotted with respect to textural, A being the strongest texture, K being the weakest texture. And what we observe is a very interesting trend. We see that insofar as the metric for indicating the potential role of anisotropy on damage by void growth is concerned, there is a non-monotonic behavior that we see. Strongest textures seem to be resistant to void growth. Similarly, weakest textures seem to be resistant to void growth. But typically what we observe in experiments are these intermediate textures, which seem to be quite susceptible to damage by void growth. In fact, textures like E, F, and G are typical of experimental textures when materials are processed by rolling. And so that tells us something about what we need to do potentially in the context of processing these materials to get our materials to be more damage tolerant. On the other hand, failure by shear instability seems to be all over the place. In fact, that might be the more demanding or more constraining aspect of how a material might fail. And you can see that most materials would have shear instability along one of the two planes of shear localizations. And so what we can do now is because both these indices or metrics are defined for the same set of textures, now I can remove the x-axis and plot something like a failure map. So on the y-axis you have a shear anisotropy ratio for a given texture. On the x-axis you have the AED index, and anything that falls in this orange zone, which means that shear anisotropy ratio being less than 1, uh, which is indicative of shear resistant material, and AED index greater than 2, which is indicative of a material that is resistant to void growth, is this orange zone. And materials with anisotropy, crystallographic anisotropy, and texture that fall in this orange zone would be of interest to us as damage tolerant materials. And what you see is that for a typical magnesium alloy like AZ31, there are fewer combinations of that you can really play with, apparently right now. At least this is preliminary work that we have done, where we can get both to be working to our advantage. On the other hand, if you have a material that is slightly more anisotropic, then the situation is a little more forgiving, in the sense that you have more range of textures that may play out to our advantage in constructing macroscopic responses that are, or designing macroscopic responses that are more damage tolerant by designing microstructures in the context of their textural processing. So with that, I will summarize this, and the future work that we are planning to do is to understand, or we are already doing some of this work, is at the single crystal scale. We want to look at how void morphology affects the crystallographic growth of voids under more general stress state, not just tensile loading states, and then hopefully take them to a level where we can construct single crystal porous yield functions. I mean, that's a more distant hope that we have at this point. But at the same time, we are also taking a parallel approach, which is more of a reductionist approach, to say that, well, ultimately for these materials to be implemented in practice, we need to have theories and constitutive models that are more reduced order models that can incorporate some of the features that we observe at the single crystal scale or at the crystallographic scale, and still be able to model failure and damage processes with reasonable good accuracy. So with that, I will stop, and I'll also welcome you all to University of Houston if you are in the neighborhood, or if you want to consider, particularly undergraduate students who want to consider joining University of Houston as graduate students. Happy to answer some of the questions later on. Thank you. Thanks for your patience, and I look forward to your interaction.
Thank you, Shailendra. Thanks a lot for this very nice talk. Professor Narasimhan has some questions. So I have allowed him to speak. So he can ask his questions directly. Professor Narasimhan, you can ask your questions directly to him.
Yeah. Can you hear me, Sumit?
Yeah, I
Am
can.
I audible?
Shailendra, can you hear him?
Yeah.
Yes, I can hear you.
Yeah, Shailendra,
Hello,
can you hear me? Yeah, great talk, Shailendra, as usual. Very insightful. Thanks very much. I have a couple of questions. The first one pertains to the type of void coalescence, because you didn't mention that clearly in the simulations where the extension twins are activated, where your C-axis is along the primary direction, right? So once the extension twins engulf major portion of the cell, you start activating pyramidal C plus A and basal. But how are these voids going to coalesce? What do your simulations say?
As I think, so you're talking about C-axis, right?
Yes. From this mechanism plot.
Yes.
Yeah.
So if you let's look at a particular level of triaxiality over here. So that right now, and this is a bit speculative in nature, what I think is going to happen beyond this. So we pretty much stop our simulations after this, because there is a significant amount of distortion of the finite element mesh at these sharp corners. Our simulations tend to stop, but we hit the criterion, the Koplik and Needleman criterion for onset of void coalescence just before this sharpening occurs. So one way of thinking about this is to say that, well, the void is going to grow further and it's going to cause intervoid ligament necking. But what I think is potentially likely to happen is that the sharpening of these voids might give rise to, and remember that there are twin boundaries at this sharpening region. Those twin boundaries might end up cracking. We have done some very preliminary work on trying to figure out, not in the crystal plasticity sense, but in an isotropic sense, what happens if we have a competition between intervoid ligament necking versus intervoid ligament cracking. And those simulations do show us that there is a certain ratio of stress, the initial yield stress to the second level of yield stress that we see in these. So let me show you this, what I'm talking about. So if I talk about this yield stress, where the stress suddenly shoots up, and the saturation stress, we find that there is a certain critical ratio of these two stress levels, beyond which your material will transition from ligament necking to ligament cracking, and essentially cause a brittle type manifestation of fracture. It will suddenly fracture rather than more graceful coalescence phenomenon.
Right. The reason I asked that question is the 2D simulations which we had done, analog of this using cylindrical voids, they show actually shear localization,
Right.
essentially caused by pyramidal C plus A. But the 3D ones are not clearly indicating that. But as you said, it could be twin-induced coalescence that could possibly take place
Right.
in that situation.
You're right. We did not observe any shear localization in this case.
Right. Yeah. My second question was in the situations where you initially showed the results of Wilkinson, where you have these elongated, you called it twin-induced voids. Okay, I would prefer to call it twin-induced cracks rather than there is a conceptual problem between whether it's a crack or a void. I mean, now how would these voids grow? Because you so far don't seem to have done simulations where you have taken an initially a non-spherical shape for your void. I know that Amin has done this work for other materials and Shyam has been doing this. But in the context of magnesium, what do you think would happen if you put a void which was ellipsoidal, let's say, in the initial shape? And then how would it grow and coalesce? Will it like flatten out completely, or can you comment on it?
Right.
From the work you have done?
Actually, you bring a very important point to the table. In fact, we have done those calculations. My most recent PhD student who graduated, Padmeya, he has done those calculations fully in 3D, similar to the spherical case that I presented over here. We're just about writing up that paper now. But we do observe that once we start start with initial oblate voids, those they respond well. The the quantitative details are quite distinct from the ones that we observe for spherical voids, but if you are in the intermediate oblateness of the void, their qualitative responses are quite similar to the ones that we observe over here. Only when you get to sufficiently oblate voids do we start seeing significant repercussions of the sharpness of the void over there in terms of the qualitative responses. We do see, in fact, at some levels of triaxiality, we see that even under prismatic loading conditions, the material actually responds as if, I mean, the macroscopic stress strain response actually looks as if the material is heavily twinned. And in fact, when we look at it from the microscopic perspective in the context of relative activities and the distribution of those mechanisms, we observe that there is a significant amount of local twinning that occurs at those sharp regions, which is what gives rise to qualitatively different responses. But that happens for relatively large, highly oblate voids.
No, but what happens for prolate voids? Because my question was on the prolate voids,
Right.
That is the type of
Oh,
shape
good.
which you showed from Wilkinson's. You called it twin induced void. So, what is the situation with the initially prolate shapes, not
Prolate
necessarily
we have
oblate?
not. We have not looked at prolate yet. Uh, I think at least not to the extent that I can comment anything
Okay,
one
okay,
way or the other.
okay. Thank you, Shailendra.
Thanks, Nasi.
Uh, Bill Tyson has a question. Bill, your mic is on. You can ask the question directly to Shailendra.
Yes, you can hear me all right?
Yes, I can.
Can you hear me?
Yes.
Hello?
Yeah,
Yes,
you're audible.
these are very complicated simulations. You're to be congratulated on your progress. But how did you set up the simulations? Are they atomistic, or how did you model the slip twinning processes?
Uh, so no, these are not atomistic calculations. These are crystal plasticity calculations. What we do is we have this crystal plasticity model that incorporates both slip and twinning in the form of slip laws and twin evolution laws. Uh, so they are still continuum theories. They are not atomistic theories, but the constitutive laws for these slip and twin rates indicated by gamma dot alpha and gamma dot beta respectively, these are defined, or their evolution is defined by processes that we observe at the atomistic scale, either through atomistic calculations or via experiments. But the calculations are entirely continuum. And to answer the question of how we do it, we construct unit cells. We assume that there is a cell in which we have a void that is residing, and we apply fully periodic boundary conditions to the faces of the cell so that we can account for other voids in its vicinity that are also regularly spaced, so that we can account for inter-void interaction. And then we apply the desired loading state. In this case, we are applying purely tensile loading states, three-dimensional tensile loading states.
Good, thank you.
Yeah, thank you.
Yeah, Manish Vaswaya. Manish, your mic is on. You can ask your question to Shailendra.
Okay, thanks, Professor Basu. Thank you, Professor Joshi. It was interesting talk. My question is more or less on the modeling again side. Like, so in this microstructural simulation, how you model the interaction between these different activities, like between sleep and twin, and with voids.
So I kind of let me see if I can bring it up, because I kind of suppressed those slides out here, but let me see if I can bring it up. So as I said, we have these crystal plasticity laws for gamma dot alpha, which is the slip rate on a given slip system alpha. Similarly, we have a constitutive law for viscoplasticity. Basically, we use rate dependent viscoplasticity over here. We have gamma dot beta for twin shear rate evolution on a slip twin system beta. And I kind of smeared out everything in this two statements, saying that we have different rules for slip and slip twin interactions, but the details are here. So this typical slip law for any IS slip system is given by this power law, where the slip hardening of the ith slip system goes based on the expression that is given on the right, and the evolution of those hardening terms, g dot slip and g dot twin slip, is motivated from the observations in experiments or the observations at the atomistic scale. Similarly,
so this
twinning,
is like a green function, or
sorry.
So this is like a green function, or like SLB like interaction?
No. These are purely phenomenological laws, but in the context of so every material point inside your volume of material, calculates these quantities, and then the region that satisfies a certain critical condition of how much volume of twin has to be generated before we reorient that region to a twinned region is embedded into the code. So typically, based on experiments, for example, an equivalent of a material point inside a continuum is represented as a Gauss point in a finite element context. So a Gauss point represents a certain volume around it. So when a Gauss point accrues a certain amount of twin volume, the total twin volume or the total twin volume fraction, we say that that region is now ready to be reoriented, because these being computational issues, we have to reorient the regions in discrete steps rather than doing it continually.
I see. Okay, thanks.
Thank you.
Babak Ravaji has a question. You can go ahead. Your mic is on.
Okay. Thank you so much. Thank you, Shailendra. It was very beautiful, very insightful presentation. And I have one question. If you come back to slide number 22 or 24, where you are showing the relative activities.
22, this one?
Oh, yeah, this one. Oh, yeah, so this one.
Oh, wait,
so,
I usually forget about clicking it one less time. So yeah, this one, yeah.
So usually in the classic theories, please correct me if I'm wrong, we see the more ductility happens when more slip systems are active, or in the opposite way, the material behaves very brittle well when we don't have much rooms for the slip activities to occur. Mm-hmm. But something we are seeing in this slide is that, for example, for the triaxiality of 2, we see much more activities are occurring, but at the same time, we see the material behaves like more brittle. It exhibits less ductility. Can you comment on this one? Well, though we see more slip systems are active, but we see less ductility of the material. Is it kind of counterintuitive? Do you have some comments on that?
I think what you're referring to in the context of more slip system leading to more ductility probably is in the context of uniaxial loading, whereas what we are seeing here is triaxial loading state. So the void is responding to the lateral stresses as well, and the higher the proportion of the lateral stresses to the primary stress, you will see that will drive the void growth in the lateral direction, which is essentially what is going to cause the coalescence of voids, and that may although you might have large amount of slip, in fact more amount of slip will cause more plasticity around it, which will drive the voids to grow even faster, right? Especially in the context of multi-axial loading states. And so I think while what you're saying may be true in the context of uniaxial loading cases, it may not necessarily be true in the context of multi-axial loading cases. So generally, if I were to say it in other words, it's quite common to see that with increasing triaxiality, the strain to fracture actually drops quite rapidly.
Right. Yeah. Thank you.
Yeah.
There don't seem to be any more questions, Shailendra. So let me thank you for a very interesting and, as usual, very illuminating talk. With that, we come to the end of this series of webinars. I don't know whether these webinars are better or worse than in-person talks, but there is something exciting and also humbling about having people from several continents talking to other people from several continents. We have had speakers who have woken up at very early in the morning, and we have had speakers who have spoken at midnight. And it was fun organizing it. We have, as Shailendra said, we started with magnesium, we ended with magnesium again. And in between, we had talks on proteins, cells, mechanics of proteins and cells, metamaterials, simulation methods like molecular dynamics, discrete dislocation, plasticity, phase fields, mechanics of sand, mechanics of asteroid formation and destruction, soft materials, size effects, and we had even philosophical talks like emergence of time and so on in this series. In one of the talks, Amin Benzarga talked about contributions of Timoshenko to what we teach today. I don't know whether pedagogic strategies should follow Timoshenko's path or Saint Venant's, but what this series has shown is that whatever they have founded has led to extremely rich and diverse field of studies, which is spreading its tentacles into almost all areas of science. That was really, really illuminating. So I thank everybody. Thank Shailendra for his talk and all the speakers in the series. So I hope we will. I think there's a question.
Is there?
Okay. Oh no, there isn't.
So if I may just say a quick word, I think this has been an absolute joy. I should say this has been the largest audience I have ever had for any of my seminars. So I'm quite happy and thrilled about it. But also thank you to everyone for your patience. And I think this series should continue. It certainly does not supplant our, face-to-face regular interactions at conferences, as those are a joy as well. But I think this is wonderful that we have been able to do in amidst these difficult times. So congratulations to the organizing committee as well.
Thank you, Shailendra. So with that, we close this meeting, and take care, everybody.
Thank you.
Yeah, bye, Shailendra.
Bye, Sumit.